And here we are, it's the physics video lecture. Once again, physics 105B video lecture 32. And we just wrapped up rigid body motion, but a related topic and one that makes use of some of our techniques is the motion in an accelerated reference frame. So that's what we're going to do now. And that'll culminate in the Foucault pendulum discussion that we'll do next time. So this should be pretty good. Motion in an accelerated reference frame. And of course, our Earth is such an accelerated reference frame, at least we think it is. But under circumstances, we just treat it like an inertial system. Other circumstances require us taking into account that the Earth is actually rotating about its axis. So, accelerated reference frame. And let's go ahead and see how we build that up. I'm going to make use of two things. So we already have this relation for vectors when there's rotation. D prime, and the prime refers to the derivative in that reference frame, omega cross A. So we've used this before. And we also have an expression for the velocity in the inertial frame. I'll write the word out. Velocity in the inertial frame. Inertial frame. So this is what we started with when we were starting to talk about rigid body motion. So we have V is V translation plus V prime, that's that same prime we're going to use right there, plus omega cross R prime. So what we're going to do, that's right, translation V in the inertial and the rotating frame. So this is an example of this relation up here. What we're going to do is differentiate it again and get the accelerations. And then we'll get Newton's law as force times mass times acceleration. So we differentiate this thing just explicitly. So now differentiate with respect to time, with respect to time. So we have, we'll just dot equals V translation dot plus V prime dot plus omega dot cross R prime plus omega cross R dot. And now what we have to do is apply this expression to here, because we already, these are accelerations, but we have to transform them according to this relation right here. And that will give us, I have 1, 2, 3, 4. I have all 4 of those. Now apply star, so we better call that thing star. To this expression. And we can take this, that's the acceleration we're looking for. We have a translational acceleration. We have an acceleration in the primed, we have an omega dot cross r prime, oops. And this one now has to be acted on by that operation right there. And I get omega cross v in the prime plus omega cross v in the prime plus omega cross r in the prime. So now we're going to see we have two of these. So once more, acceleration, translation. In the prime system, we have I'm going to take these two first. So we have this and this right here. So we have plus 2 omega cross v in the prime system. We have omega dot cross r in the prime system, and then we have omega cross r in the prime system. So that's quite a bit of quite a lot going on compared to the simplicity of the inertial frame. Okay. But not all of these are equally important, and but for the moment, that's the actual expression. So now let's write Newton's law. Okay, and yeah, we'll write Newton's law down and then give these things names. So inertial frame, F equals ma. So m times a equals f. That's the simple form. Apparently we're going to have to subtract all of these extra terms to get the force law in the moving frame. So in the moving frame, and this is the result we're going to have to stop and ponder, we have m a prime equals m times a, so that would be, where are we right here? No, ma prime, m times a, and then subtract all of those off. Okay. So did I prime this? No, I didn't. Yeah. So ma prime, we're talking about mass times that one in the prime system, is equal to ma, which is f, minus everything else. So m a translational acceleration minus m, which one are we going to do first? Omega dot cross r in the prime system minus 2m omega cross v in the prime system minus m omega cross r in the prime system. Okay, there's a lot going on here. So this is all happening in the moving frame. So the moving frame is the prime frame. You express the force, in the inertial frame in terms of the moving frame axes if you're going to use this. Okay. So if we have some moving frame here in this, let's call this the lab frame. If you have some moving frame, then we'd have to project, say, gravitational force, the weight, onto those moving axes. Okay, but that's that term there, and all these other things are referred to as fictitious forces. They also come into play. Now, this one here is is going to be really subtle in terms of our application. We're going to talk about the Earth's rotation, and then the omega dot for the Earth's rotation about its own axis is very, very small. Okay. And these have names. Other than that, this is the Coriolis Force. And this is the Centrifugal Force. Okay, the omega cross the R prime. At some point we'll drop the primes. Okay, but right now, this is with respect to the body axes. And this is the force in the inertial frame. It would be projected onto the body axis too. Okay. So we better do a really simple example. In fact, we'll do the example where omega is equal to 0. Okay, that's going to get rid of all of these terms here. So no rotation at all. Then we're just left with mass times acceleration, F minus m, a translational acceleration. And the simplest example to understand what's going on here is just free fall. Okay, so you're in an elevator and the cable breaks, and now you're freely falling. Okay, so free fall, we have the translational acceleration is just equal to g. Okay, and of course the external force and F is also equal to mg, just like that. So if you put those together, m times a, better prime it still. Like I said, eventually we'll drop the primes probably, but right now we got the prime. So m times a prime, the force in the inertial system, is equal to mg minus mg is equal to 0. Okay. So F equals 0 in the, did I say move? Yeah, in the moving system, in the accelerated system. Okay, so that had to check out, and that's very basic. But now if you have a problem in which the rotational effects come into play, it can be a lot more complicated. So the next thing to do, I think, is to talk about the Earth, rotation of the Earth, about its own axis. So we'll leave this all up here. Okay. Yeah, okay, so we have them at the very top of the board there. So let's see what we want. Let's formulate it as a question. Does Earth rotate about its axis? And this is answered with the Foucault pendulum. But I'll set this up. I have a good sketch for this. And in fact, is Earth's surface an inertial frame? Okay. thing with the Foucault pendulum, you get a measurable result in terms of the pendulum. So let's go ahead and set this up. I have a sketch here. So what we'll do is, imagine this is the North Pole. Earth is rotating about its axis, that's omega. And if we go out along a longitude, then at this point here, we have a body frame like so. X, Y, Z. I think we have some reasonable perspective there. In fact, I'm going to tilt the Z a little more. X, Y, Z. And then we'll have a little angle alpha like that. So the Z axis with respect to the omega axis makes this little angle alpha there. And yeah. And this alpha is just pi over 2 minus theta, where theta is the latitude in radians. Okay. So if you're at the equator, theta is equal to 0, alpha is pi over 2, and if you're at the North Pole, theta is 90 degrees, pi over 2, alpha is 0. Okay, so that's right. What about this angular velocity? The claim is that Earth rotates about its axis, so it is claimed that omega magnitude here is just 2 pi divided by 1 day. And so what we want to do is set up these equations, and then we'll set them up for a pendulum. So what are we going to do? So we're going to do some restrictions here. We're going to assume that omega dot is negligible. Okay, so omega dot's negligible because the Earth is pretty massive and it's just rotating about its axis. And the day is not really changing over appreciably. So omega dot is negligible. And then the centrifugal force, also omega cross omega cross r prime, is negligible as well. Now, if you look at the direction of omega cross r prime, you'll see why it's called the centrifugal force. It goes away from the center of the rotating body. So these are both going to be negligible because omega being 2 pi over a day is very small. Which is to say omega cross r prime in the lab frame is going to be smaller than the b prime. Okay. Good. So we're going to get rid of those, and now we have a pretty simpler equation. Now we have n a prime is equal to f minus 2m omega cross b prime. So that's going to be our equation. This is going to be the gravitational force, the weight, and this is the one fictitious force. So this is the force that will act on our pendulum bob, as we usually see it, toward the center of Earth. And this is going to be the so-called Coriolis Force. And we're going to set that up, see how far we go for today. good, yeah, I'm gonna set those equations up for a pendulum. And it will be for the small oscillations of the pendulum. So let's do that in a couple of steps. We'll set them up today and we'll solve them next time. So let's call this small oscillations of an ideal pendulum, or of a simple pendulum. So first of all, just x, y, and z components. So m, x, second derivative, and yeah, I'm dropping the primes now. Drop primes. Fx minus 2m. And now, we can get these cyclically. We have omega cross b. So omega y z dot minus omega z y dot, and on through my second derivative f sub y minus 2m omega z x dot minus omega x z dot, and in z second derivative f z minus 2m omega x y dot minus omega y x dot. So for a simple pendulum, okay, now we're just on Earth talking about our simple pendulum, and so we don't have to worry about that for the moment, but just to analyze this thing, here are x, y, and z, our pendulum, you could say is suspended right here, okay, and its motion is going to be in the xy plane. Primarily in the xy plane, because for small oscillations the z excursion is quadratic and the x and y excursions are linear. So motion is primarily in the xy plane. Okay. This is the primed plane. This is on, this is on Earth. This is right here. I've dropped the primes though. So that means I can focus on these two equations. And the Fx and Fy are really the restoring force, effectively the Hooke's law restoring force. So, first thing we'll say is we can ignore z dot. Second part, use these first two equations, star, and that's what I'm going to end with. We're going to go ahead and rewrite these. I actually would like to have everything on the board, but I can leave that picture. I'll leave that picture and just open up this half of the board. So here's what we're going to have. Equal to fx plus 2m omega z y dot my second derivative of y minus 2m omega z x dot. Let's see where that came from. Okay, the z dots, first of all, this equation we're going to ignore. because the motion is essentially in the plane. Okay. For that reason, the z dots are negligible as well. So we have minus 2m times minus, so we get the omega z y dot right here, and omega z x dot right here, okay? So that's the kind of simplification we need to tackle this problem. So again, what we're looking at now is a pendulum that can swing in the XY plane essentially, and right, suspended up there. And if there were no rotation here of the Earth, these would be the equations, and this would essentially just turn into a Hooke's law in either case. Okay. So the new effect is going to be from here. So what we'll do next time is solve these. And we'll call them double star. And once we get this result, we're probably going to want to build one of these things. So let's keep that in mind too. Okay, so that's where we'll leave it. See you guys next time.